We're going to talk about Newton's third law today. And but first I'd like to review the Newton's first and second law. And then we'll talk about the third law, which is called the law of interaction. I do want to talk specifically about normal forces and the gravity force, although we're going to do gravity in more detail in the next assignment. And then I'll briefly talk about an interaction diagram. And it's going to be a little tough for me because I'm going to try to switch my brain around to do it the way the book does it. But we'll give it a shot. Okay, so Newton's first law was the law of inertia. And it basically said that objects don't change the way they're moving unless you force them to. If an object's at rest, it will remain at rest. If it's in motion, it will remain in motion with constant speed and direction forever, unless something from the outside acts on it. An action is taking place. An agent, some outside agent, is doing something to it, applying a force to it in some way. Now, Newton's second law basically kind of defines how that force is measured and the effect of that force. That if I have a net force on an object, that object will accelerate. But the amount of acceleration depends on the mass. That's the inertia of the object. The more mass something has, the harder it is for that force to accelerate it. If you double the mass, you cut the acceleration in half for a given force. So, and we said that the net force was what we got when we summed all the forces acting on the object. So this is Newton's second law and is a very important law of nature. Probably the most important law of nature for us in our everyday lives. Now we're going to get to the third law. And the third law is called the law of interaction. Now, and here's an interesting story. About a little over 100 years ago, if you were to open a newspaper and go to the sports page, there were 3 major sports that were covered 100 years ago. And 2 of them were not basketball or football. There were 3 major sports. One of them was baseball. Nope, not soccer. Not rugby. Boxing. Boxing was one. The other one was horse racing, which isn't really relevant to what we want to talk about. But boxing. Boxing was a major sport. Probably the major sport, even more popular in some ways than baseball. And if you think about it, mainly guys, although women are boxing now, which is fine. That's if they want to do that, I don't want to do that. But we should all be free to do what we want to do. But let's say 2 guys in a village want to fight. They're mad at each other. They're fighting over something, and they want to fight. Well, you don't want these people to kill each other. So what they would do was they would kind of set up some kind of organized rules so that they can get it out of their system. Of course, what happens when anybody has a fight? I mean, if there's a fight out on the quad, what happens? Everybody runs towards the fight. You'll see teachers running towards the fight. Are they trying to break up the fight? Well, that's what they'll tell you. But really, we just want to see the fight, right? Let's see who wins this one. All right. Now, so it's very entertaining for some sick reason to watch people fight. I don't know. Well, so they eventually, people started taking advantage of that, and you get two people who were, the first professional athletes were really boxers or fighters. And so they would pay them. And now, a boxer, the first professional athletes, well, in those days, the original days, they didn't have gloves. They didn't wear gloves. They didn't have boxing gloves. They just were like bare-fisted fighting, okay? Well, in those days, fighting was actually safer in a way. Because when you're going to punch somebody, here's my massive fist, all right? Actually, a fist, even of a big, strong guy, skinny little bones, skinny little fragile bones in your fist. Okay? Now guess what the hardest bone, set of bones in the human body is? The skull. Okay? It's protecting the brain. So if they were to punch each other in the skull, the guy would have a knot on his head, but the other guy would have a broken hand. And if you're a professional fighter and you have a broken hand, you've just lost your livelihood. So those first original guys that would box, but they didn't have gloves, it was all body blows and stuff. They didn't really punch each other. They would slap each other in the face and stuff, but they, it really, they wouldn't punch each other in the skull because you break your hand. Well, then they started wrapping their hands, wrapping their knuckles, putting gloves on it. And then they started putting stuffing in it. Now, you might think that the boxing gloves are to protect the head or the body of the person getting punched. Nobody cares about their face. They don't care about their face. What do they care about? Their hands. The boxing glove was invented to protect the hands of the boxers, not the face of the person getting hit. And so the boxing gloves evolved over time to become so efficient at protecting the hands that now boxers could punch as hard as they could at somebody's head, which ruined the sport. Because now, when they would punch the head of somebody, you were giving them concussions. In the original boxing, they could go, dozens of rounds, and somebody would collapse, but they really weren't knocked out. They would just fall down out of exhaustion. But then they started hitting each other in the head, and they would knock people out, and that's a concussion. And a concussion over and over again causes brain damage. And they would have guys that they called them punch drunk, being punch drunk. These fighters that would fight over and over and over and over again. Well, it was just brain damage. And and they would die young of brain damage. It's very sad. Well, that's all because of the law of interaction. I'm sure some of you, most of you who suffer from testosterone poisoning do this, but I think some other people do as well. But if you get mad, you punch a wall, who's going to win?
The wall.
The wall's going to win. First of all, the wall doesn't care. It has no feelings. It's an inanimate object. But you can hurt. You're probably going to hurt your fist if you punch a wall. Because here's what the law of interaction says. For every force on one object, there is, underline is, there is an equal force in the opposite direction oops, I don't want to put that in parentheses, on another object. This is a big deal. If you punch a wall, you push the wall to the right, but the wall applies an equal but opposite force to your fist to the left. Okay? So, for every force on one object, there is an equal force in the opposite direction on another object. This is a law of nature. This is true. This is not fake news, people. This is true. Okay? So these laws all kind of interact, work together. These are called Newton's 3 laws of motion. Inertia, oh, this is the law of acceleration. So, let's start off with the most simple idea. And we're going to draw what's called an interaction diagram. Here is my little toy apple. And it's just going to sit here on the table. And this is it. This is all we're going to look at right here. See, physics is exciting stuff. Now, let's think about the forces, and we're going to draw what's called an interaction diagram. So I'm going to draw a little diagram here. Here's the ground. The ground is part of the earth. Here's the table where I'm sitting. I'm just going to draw it as a rectangle because it's just easier. And here's the apple. Well, it's not a real apple, right? It's a foam rubber apple, but there's my apple. Ground. Table. Apple. Okay, we'll just call it an apple. Okay, now all of these objects are interacting, which means they are applying forces to each other. Now, if I hold this apple and I just kind of hold it here, right, I'm just kind of hanging it, Earth pulls this apple down, doesn't it? And we call that the force of gravity. But here's the thing. The Earth is, even if the Earth isn't in contact with the apple, it's pulling it down. It's called a force field. We live in a field that's called a field force. And what's actually happening, and it's happening to us, we live in a force field, a gravitational force field. Earth is so massive that it actually distorts this fabric of space around it. And it creates like the slope of like a hole, no, not a hole, it's like trying to dig a hole in 3 dimensions, though, not in 2 dimensions, it's a hole, and we're trying to fall into that hole. Okay, and we call that the force of gravity. Einstein figured out it was the warping of space by massive objects. You actually create your own little gravitational field. It's just that it's very, very, very weak because you don't have very much mass. But in any case, the Earth pulls down on the apple. So here's what I'm going to do. I'm going to draw a bunch of arrows here, and it's going to get really confusing. All right. This is the force on the apple. Do you see how I put an A subscript there? The force on the apple by what?
Gravity.
By gravity, but what causes gravity?
Earth.
The Earth. So look at the order here. The force on the apple by the Earth. So the first subscript is the object. The second subscript is the agent that is applying the force to the object. So it's the force of the on the apple by the earth. Does everybody see that? But what does Newton's third law say?
That for every force on an object, there must be an equal force on another object in the opposite direction.
Exactly. So for every force on one object, the apple, there must be an equal and opposite force on the other object. So guess what? You may not have realized this before, but this apple right here is pulling up on the earth. So here's the earth, the whole planet, 9,000 miles in diameter. The apple is pulling up on the earth. This is the force on the earth by the apple. And these two forces are equal in magnitude but opposite in direction. This shows the interaction between the apple and the earth. Make sense? But what else is the apple interacting with? Because if it was just the earth, what would happen? The apple would fall towards the earth. Would the earth fall up towards the apple? Yes, it would. The earth would fall up towards the apple. But the earth has so much mass that the acceleration of the earth up towards the apple is just so tiny that we can't even observe it. But it is there. It's just a trillionth of a trillionth of a trillionth of a meter per second squared up. Yeah. Well, in the meantime, the apple is falling down with 9.8 meters per second squared down. Right. But it is there. It does exist. It's just that we don't notice it because the apple has so little mass, its gravity is so weak that, but equal and opposite forces. Okay? Now the table is holding up the apple. And this is the force of the table, the force on the apple by the table. That. Okay, I didn't mean that. Force on the apple by the table. So this is the object we're looking at. And this is the agent that is causing that force. Well, if there is the force of the table on the apple here, or the apple by the table, there must be an equal and opposite force. And this is the force of the on the table by the apple. Okay. Now there are other interactions here. There's the earth pulling down on the table pulls up on the earth. Okay. The ground pushes up on the table pushes down. The table pushes down on the ground. But I'm not going to draw those because this is messy enough. I really mainly want to focus on the apple. Now, what if I really mainly want to talk about what's going on with the apple? I'm going to draw the apple like this. And so here's the force on the apple by the earth. And this is the force on the apple by the table. Now this is an interaction diagram. This is what we call a free body diagram. A free body diagram is when I take one of the objects out of the interaction diagram and just look at the forces on that object by outside agents. In this case, the earth on the apple, and here the table on the apple. Now, do these have to be equal and opposite forces? No, they don't have to be. Because what if the table was like on an elevator and we were accelerating up or something like that? What if there was an acceleration? Then these forces could be different. But what if the apple is at rest? If the apple is at rest, the force on the apple by the table and the force of the apple by the earth, they will be equal and opposite because they have to cancel out. But these two forces, listen very carefully, because this is where we're going to get hard. It's going to start getting hard in here. These two forces are by two different outside agents, the table and the earth. They are not the interaction forces. Here's the force on the earth by the apple. Here's the force on the table by the apple. Those are the interactions of these two. Okay, now I'm gonna let this sink in for a little bit. I want you to really think about this. By the way, the book is excellent on this subject. I want you to read the book. The problems I'm giving you are pretty easy, and I want you to spend 15 minutes, 20 minutes, read the book. They do an excellent job explaining this part. Actually, I've been really impressed with their new book. So, now, this it's kind of awkward to say the force on the apple by the earth. So we're going to call this the force of gravity. Okay, the force of gravity. But make sure that you understand it's an interaction between the earth and the object. It's the force that the earth applies to that object because that object is in the earth's gravitational field. Now this right here, we're going to call this, we're going to call this, let me check what the book is. Yeah. I have 3 different books, and they all do things slightly differently, and it drives me crazy. But we're going to call this F sub n. The force of the table applies to the apple right there. We're going to call it F sub n. And this is the normal force. The normal force. Now, this is an unusual name. What do we mean by normal? Normal. Like in everyday language, that person is very normal. I'm of normal intelligence. I have normal looks. I'm so normal, I'm just boring. Okay? Or somebody is very abnormal. That means they are... No, that's not what we mean by this. We don't mean that. Normal in mathematics. Does anybody know in here know what normal means in mathematics? It means perpendicular. In fact, I wish instead of calling it the normal force, we called it the perpendicular force. That would make more sense to me. It would be easier to teach. But every textbook I've ever seen, every physicist I've ever talked to, we all call it the normal force. And the normal force is the interaction between two surfaces. And here we have, let's take a look at this. Here's where the apple and the tabletop are interacting. So here's the surface of the apple, and here's the surface of the table. And they're applying their interaction to each other. This is the normal force. This is the table on the table on the apple. But this is also a normal force. This is the normal force of the apple on the table. They're equal and opposite. They're interaction force. But we're drawing a free body diagram of that. And notice of just the apple. So that's why we put it in a free body diagram. But these forces are perpendicular to the surface. You have two surfaces pressed together. In this case, here's the apple. Is the bottom. There's the bottom surface of the apple right here, and it's on the surface of the table right here. So it's that interaction. And the normal force, the reason they call it the normal force is that it is perpendicular to the surfaces. Okay? So that is, so that's what you need to know. So just to review, and by the way, the book has some examples and problems and so on, so definitely read the book. But the third law is the law of interaction. For every force on one object, there must exist somewhere in the universe an equal and opposite force. That is always true. And we can draw a picture showing that interaction. We can use these subscripts as a force on the apple by the table, the force of on the table by the apple. And then we take that interaction force. Sometimes we would just draw a picture of one of the objects called a free body diagram. We're going to cover that in more depth later on. And the interaction between two surfaces that's perpendicular to those surfaces we call the normal force. So we have normal force and we have force of gravity. I think the book uses capital G for the force of gravity. I will never be able to do that because I've been doing this stuff for 35 years and we always have used lowercase g. But I think you can handle that difference. Any questions? Okay. That is all.